Hello everyone, my name is Hala and I am pleased to present the challenge we've tackled this year, Starcop 2.0, building on and extending the amazing work of previous FDLs, Starcop 1.0. Our team consists of 3 researchers, Luca, Maggie, and myself, guided by Laura, Giacomo, and Chris. Over the past 150 years, the average temperature of our planet has increased by about 1.2 degrees Celsius. Most of this warming has happened since the 1970s, with the last decade being the hottest on record. But what's actually driving this warming? Let's look at the biggest culprits. Our planet is constantly subjected to anthropogenic greenhouse gas emissions that drive global warming. Among them is methane, one of the most potent. Though it lingers in the atmosphere for only about 12 years, far less than carbon dioxide, which can remain for over a century, methane's warming power during that time is far more intense. Impact isn't just about how long a gas stays, but how strongly it hits the planet while it's here. Thanks to satellites equipped with hyperspectral imaging and AI models capable of processing enormous amounts of data, we can now detect and even track these emissions directly from space. This is transforming how we find leaks, trace emissions to their sources, and hold polluters accountable. This is possible as every gas interacts with light differently, absorbing specific wavelengths and creating what we call a spectral signature or fingerprint. Hyperspectral and satellites measure hundreds of bands of light, and when a signal matches a known fingerprint, as we can see in this example, we know exactly what gas is there and where. This is an example of how a satellite observes our planet. To the naked eye, even from space, it all looks fine. But if we look deeper, combining those bands at the right ratios, suddenly the invisible becomes visible and the methane plume gets revealed. The real challenge is knowing when and where to look in a timely manner to ensure fast action. I will now hand over to Maggie, who will present our proposed solution.
Thank you, Hala. We approached this challenge by utilizing the growing constellation of satellites that are available to us from recent missions. We introduce a tip and cue system, where the tip satellite performs fast and accurate plume detection, and once a plume is detected, it then alerts a cue satellite, which then performs more sophisticated tasks, such as providing precise plume segmentation, as well as predicting the methane concentration. This information can then be transmitted to the ground station, informing stakeholders downstream. And this will facilitate an early warning system for greenhouse gas emissions and leaks. The highlight of this project is the implementation of machine learning on board these 2 satellites, bypassing the intermediate step of transmitting images back to ground, which is time-consuming. One of the challenges specific to onboard machine learning is auto-rectification, which is a process that corrects image distortion. The satellite usually observes a region of the Earth at an angle, and it sees an image like this. However, due to the tilt of the satellite and the curvature of the Earth's surface, and also the elevation in the features on the ground, like the ones in this image, the image it observes is in fact distorted. And auto-rectification is a transformation that corrects for these effects and gives us the auto-rectified image. And we derive this transformation in both directions, creating 2 ML-ready datasets, the auto-rectified and the unauto-rectified images and the plume annotations. The previous Starcop 1 project used the auto-rectified approach, whereas the unauto-rectified approach is completely novel and more suitable for onboard implementation as it bypasses this correction step, therefore speeding up the inference time. Using our datasets, we have trained 3 machine learning models for the TIP and Q satellites separately. The TIP satellites first performs plume classification using a vision transformer. For example, the ground truth of this large image contains a methane plume, and the classifier is able to identify the tiles that contain parts of this plume, such as this one, with high confidence. It triggers the TIP satellite to then alert the Q satellite, which then performs plume segmentation using a UNet architecture. and we see good agreement between the prediction and the ground truth. We chose to quantify this agreement using the intersection divided by the union between the two shapes, which yields around 67% for this particular tile. The Q satellite also predicts the plume concentration using a UNet architecture starting with weights from training on a larger and more generic image dataset, ImageNet. And the predicted concentration has a mean square error of around 10% of the maximum concentration in this plume. And the model also smooths out the missing pixels in the ground truth. The pixel predicted with the highest concentration can also inform us on the plume origin, which is a valuable piece of information for stakeholders downstream. And now I pass on to Luca, who will discuss the impacts of our research.
Thank you, Maggie. Hi, my name is Luca. So deploying AI models in space is a complex task, as spacecraft have limited resources, such as computational power, memory, and energy budget. For this reason, we converted our model into ONNX format, and we will test them on hardware that simulates spacecraft capabilities. In addition, our preliminary results show that we are able to compress a vision transformer from 41 to 14 megabytes, achieving an inference time between 5 to 10 milliseconds for single hyperspectral images. So, after training and evaluating the models, we want to release to the scientific community the two machine learning-ready datasets that Maggie previously presented, specifically the orthorectified and unorthorectified datasets, with the latter representing a more realistic scenario for onboard processing. This dataset will be composed by images and corresponding plume masks that can be directly fed into machine learning models. Moreover, we are going to release the AI models for greenhouse gas detection that we optimize for onboard spacecraft processing. Not only will we test them on hardware characterized by limited resources, but we will also benchmark their inference time, memory footprint, and power consumption. In the future, we foresee AI-powered satellites cooperating for fast detection and alert of greenhouse gases. To summarize, firstly, the TIP satellite detects a plume of gas, and it then sends an alert to the Q satellite. Secondly, the Q satellites acquire more detailed information about the plume, and it then sends the location, extension, and concentration of the plume to end users, such as the United Nations International Methane Emissions Observatory. In this way, data-driven information about greenhouse gas leaks can be collected as soon as possible and be used by policymakers to reach the goal of reducing the net global greenhouse gas emissions to limit climate change and its associated extreme events. That's all from our side. I would like to add that this work wouldn't have been possible without the support of FTL, funders, and partners. Thank you.